Back, everybody. Today, what we are going to do is talk about the change of quantifier rules. So basically, we are going to have quantified statements, and we're going to talk about equivalent statements. So these are like rules of replacement, like we've done before. So let's just get straight into it and look at some of these changes. Now, if I told you, right, if I told you that everything on this planet was cool, that would be like saying that there does not exist something that isn't cool, right? So that's an example. Changing a quantifier, I said a universal quantified statement, everything is cool, and I made it an existentially quantified statement, there does not exist something that is not cool. So there's a little example, and that's going to lead into our first change of quantifier rule that I want to show you, is that if we have a statement that looks like this, for all x, fx, right? Something that just looks like that. And that is equivalent to saying that there does not exist an x that is not fx. So we'll say fun for f, right? If everything is fun, then that means nothing is not fun. We cannot find something in this universe that is not fun because everything is fun. The next change of quantifier I want to look at is if we say not for all x, f of x. Not for all x, f of x. So what I'm saying that it's not the case that everything is fun. Well, if it's not the case that everything is fun, I think it makes sense to say that there exists something that is not fun. We could find an example of something that is not fun. What I'm doing when I'm changing these quantifiers, I want to highlight this, is I am pushing our tilde through the quantifier to the statement. And in doing so, I am switching the quantifier from universal to existential and vice versa. So, like with our second example, I have not for all x, f of x. I'm pushing this quantifier right through here. So it goes right there. It negates our statement, and then we switch the quantifier. And then you could see it in the reverse direction for our first example. If I push this tilde through right here, I get not f of x, so we could just double negate that and say fx. And then I flip the quantifier, which yields the for all x, fx. So I just wanted to highlight that if you have a statement, the equivalent statement would be negating your statement and then flipping the quantifier. You got to push that tilde through and then flip the quantifier. So now we have two more that I would like to look at. What if we have there exists an x, f of x? So what I'm saying is there's something in this universe, and that something is fun. How could I swap that to a universal statement? There's something in this universe, and it is fun. That is equivalent to saying that it is not the case for all x, not f of x. So in English, there exists something that is fun. This is saying for all x, nothing is fun, but then I negate that. So it is not the case that everything is not fun. Why is that true? Because there exists an x that is fun. Hope that made sense. If it didn't, it will eventually, hopefully. We only got one more, so don't stress it too much. We're going to negate our statement now. We are going to say, not there exists an x, f of x. So it is not the case that something is fun. It's not the case that something is fun. That sounds like for all x is not fun. Everything in the universe is not fun. So those are our change of quantifier rules that we can use in our proofs and our shorthand. So when we're writing this out in a proof, we'll write CQ. That is our change of quantifier. Now this is all fine and dandy to talk about in theory, but what about in practice? Let's do an actual proof where we'll use this change of quantifier and all of our other wonderful rules of inference. So what will our premises be? Our premises are going to be there exists an x, hx and gx, and then we'll say for all x, lx. That's our first premise. I know, complicated. Our second premise will be not lm. And then the conclusion we would like to reach, let's change up our color for this just to make it different. The conclusion we want to reach is for all x, h of x, then g of x. H of x, then g of x. Is that what we want? I think that's what we want. No. We want h of x, then not g of x. So that is what we are striving for. And before I actually start doing this proof, let's just look at the premises and the conclusion. At least to me, this does not look simple. This does not look obvious. This does not look like something that I will get on my first try, and that's okay. I just want to say that if you're taking this class, symbolic logic, and you're struggling with these proofs, it's okay. There's not a single person on this planet who is expecting you to get your proof right the first time, or even the second time, or maybe even the third time. We have a lot of different rules of inference, and there's not only one way to get to the end. There are multiple ways to get to the end. So no one is expecting you to find them on your first, second, maybe even third try. These proofs, sometimes they just try guessing and checking, trying something, and if it yields nothing, you don't get hung up over it, you erase it, and then you start again. So when I go through this proof right now, I hope no one's wondering to themselves like, oh, how could he think of that the first try? Or I could never think of it the first try. I didn't think of it in my first try, but I'm just showing you it now. With that said, let's get into the proof. So, again, not my first thought, but what I'm thinking we could do. I mean, there's not much we can do. I guess we can existentially generalize line 3. I think that's like the only thing we can do. I don't really see anything else to do. So let's just try that, right? Let's make sure we have the right color chosen. We have blue, great. All right, so line 3, let's just existentially generalize. So we have there exists an x such that it's not L of x. So that comes from line 2 and existentially generalizing. Now again, there's really not much to do. We are, however, learning about change of quantifiers, so that's probably relevant. And if we look at our second line we have right here, we have there exists an x, not L of x. So that's equivalent to not for all x, L of x. Let's just try that. Not for all x, Lx. There we go. That comes from line 3. And the change of quantifier rules. Okay, cool. Now I'm starting to see something. If you'll notice on line 1, we have for at the end of our conditional says for all x, Lx. We have not for all x, Lx. So we can modus tollens this, right? So let's try that. Let's see if that gets us anything. So from lines 1 to 4, what we get is not, that does not look like a tilde, not, there exists an x, hx, and gx. So that came from line 1, 4, and modus tollens. All right. We're getting somewhere. We have h's and g's, and that's what we want in our answer. Again, not much to do, so let's just do what we know, do what we can. Let's push that tilde through and change our quantifier on line 5. That is going to yield a for all x. All right, that's it. That's in our conclusion, so I think we're getting warm. Let's negate our statement, hx and gx. There we go. So what does that come from? That's line 5 and a change of quantifier. We could try De Morgan's, right? We know what De Morgan's rules are, right? So let's do for all x, and then this will become not hx or not gx. And that came from line 6 and De Morgan's. And now I think the least obvious jump that we're about to make, for some reason, implication is just a rule of inference that's not at the top of my mind. but it seems to come up a lot, so maybe it should be. That'll be my tip to you. Remember implication, because that's what we're going to do right here. Implication tells us that line 7 can be written as, for all x, if hx, then not gx. That comes from line 7, implication, and we're done. That's exactly what was desired, what we wanted from the beginning. So that's how you use the change of quantifier rules in conjunction with our generalizations, our instantiations, and all of our other wonderful rules of inference. If you made it to the end of this video, thank you for watching. I really appreciate it, and I truly hope you learned something.